what model do you want for conventional one. If you select the downflow model, you tell me what size of downflow model you want. Good. Homework is still not this week, I think. Sometime later.
Monday.
Right? Okay. Sign up sheet. Can you give them sign up sheet? Please rotate sign up sheet. After everyone sign, let me have it. Let me review you one more time. Isobaric is constant pressure, isothermal constant temperature, isentropic constant entropy, and isochoric means constant volume. Good? Too easy. Okay. We talk about how the reciprocating compressor works, right? What happened to pressure? What happened to we haven't talked about what happened to temperature yet. Typically, when we add work into the system, temperature go up. Okay? When we add work into the system, temperature go up, and we are about to show you mathematically. We talk about the closed system for first law of thermodynamics. Everyone's good on that? Okay. Next one. Same thing, but this time is steady state. Okay. Marcos. What is G sub C for?
What is what?
G sub C, 32.2. What is that for?
That is the gravity built in a field units, I guess.
So if I write this equation in SI, do I have G sub C?
No, that in SI would be 9.8.
So if I write in SI, that value will be
9.8
or 1. You want 1? 1. Not 9.8, okay. The reason that sometimes you have seen something like G sub C, sometimes they write G, sometimes they write G sub C. They have the same value, okay, 32.2, they are the same. The difference is when they write G, G is real gravitational value, 9.8 or 32.2, okay. When they write G sub C is a conversion factor. The reason that you need conversion factor because typically energy in SI is Newton multiplied by meter, right? Newton meter. So Newton in field unit, it should be power mass per second square multiplied by foot, right? Power mass foot per second square. That term. So that is equivalent to Newton. Okay. Newton meter means that term multiplied by one more foot. So it will be power mass foot square per second square. However, customary people don't like power mass foot per second square. They like to report work in power force foot. Okay. So whenever they report in power force foot, that G sub C is to convert from regular force to power force. Okay. Instead of power mass foot per second square, we divided by G sub C, then it's become power force. So that is the only reason. Other term like W, it is in the form of power force foot. Okay. So this means that G sub C is not real G. In SI, we just delete that because we report everything in Newton. We don't report everything in like power mass or something, or kilogram force or something. We don't do that, right? So we just do Newton. So in the SI, that the term just gone. Look at this Q and W. Look at the unit. The unit is still power force foot. Okay, the unit is power force foot. So the unit left hand side and right hand side has to be the same. And this equation is for steady state. It is not about no mass in, mass out anymore. Previously we have closed system, right? No mass in or out. This time we allow mass to go in and out, and we do the conservation of energy over a control volume. Okay. When you see this, okay, next step, we try to derive the ideal isentropic horsepower. In that case, we assume no change in the elevation. Okay, the change in the elevation is negligible. If you think about it, compressor is sometimes big, right? And there's a little bit of change in the elevation, but that doesn't matter. The energy gain or energy change due to the change in the elevation is a lot less compared to other terms. Okay, so we can neglect that, and we try to get the ideal horsepower. Okay, so you have learned earlier, right, that we can get reversible adiabatic. That line, that is the ideal case. For something that is real case, you have to do more work. Okay, so when we assume adiabatic process, reversible, adiabatic plus reversible equal to isentropic. Okay, next to Marcos, what is his name on your right hand side?
It's Eric.
Eric?
Yeah.
Okay. So isentropic mean what? What is constant?
It's constant entropy.
Entropy. Okay, very good. We try to do get the equation for isentropic horsepower for ideal case. So this is the assumption Q equal to 0 and S is constant. Okay, reversible process, reversible and adiabatic. Adiabatic means no heat go in, go out. Okay, we neglect the force due to friction, neglect the change in the kinetic energy. So we assume that the speed of that gas molecule doesn't move a lot faster or a lot less. Okay, and we know that H is U plus PV. So after we neglect many terms, what you get is this one. Delta H is equal to minus W. So W, let's go back. W is force by work done by the system. Okay, work done by the system is W. Okay, and U is the change in the internal energy. This thing suggests if we have work done on the system, so W becomes negative, minus of negative value become positive, right? So if we have work done on the system, enthalpy go up, or it become hotter. Okay, temperature go up. So when we compress it, the temperature go up. Okay, and this is the way that we can estimate the ideal horsepower or the amount related the work and heat together. Okay, so we get this equation: delta H equal to N delta small h. Small h is molar specific enthalpy. So it's BTU per mole, per bar mole. Okay. And we have delta H is heat or enthalpy increment of the system, right? So if we have work done on the system, we have negative work, then delta H go up. So this means that if we start at point 1, we do something to the system, work on the system, put more work to the system, it becomes hotter or more enthalpy. So we do this at constant entropy. So this graph is a plot between entropy, that S, and enthalpy, H. Good? So when we go up straight like that, S is constant. So we said, okay, this is a theoretical pathway when we go from 1 to 2. We move up at constant entropy. Okay. This plot, you see that this curve thing is like pressure and that thing is temperature is somewhat difficult to read, and we will go more into it. The only thing that you need to know maybe this thing is enthalpy and that is entropy. Okay? Let's do example so that we learn more about this. What is the theoretical horsepower consumed in compressing 1 million cubic foot measured at 14.73 psia and 60 degree F? Okay. First thing, you see this number, that is the standard condition that they use. They spell it out because several different locations define the standard value differently. So at Texas, you have one standard value. Somewhere else, have another standard value, and I think I recall that if we have to prepare several reports for federal and state, it will be different reference point. Do you have anything to add on this? The reference condition. Okay, it can change, so we better write it out what it is. It can be something else. Okay, so we have 1 mmSCFD, and standard condition is 14.73 and 60F. And we want to get theoretical horsepower that can do the compression and go from 65 to 15 psia. Okay. Initial temperature is 80. Okay. The question is, what is the theoretical horsepower? Next one is, what is the discharge temperature of gas? So, assume the gas gravity of 0.6. We know that when we compress it, it's going to be hotter, right? You agree? We compress it, it's going to be hotter. So if your answer is lower than 80 F, then it is wrong for sure and should not be forgiven, okay? It should be hotter. Next step, what we do is, we look at the chart, okay? When we do theoretical horsepower, entropy or S stay constant. We look at the entropy of 0.1 at 55 and 80. Okay, let's move to this one. You see, this is a PSI in absolute pressure. 10,000 line is that thing. That thing is 10,000, 5,000, 2,000, 1,000, and 14.7 is that line. Okay. Now let's take a look at temperature. 32 Fahrenheit, that curve is 32 Fahrenheit, constant 32 Fahrenheit. 500, that's my 500, 500. Okay, that line is 500 Fahrenheit. So temperature line go from left to right, like that. Pressure go from top to bottom. So first thing is we try to locate 65 psia and 80. Okay. Where is my 65? So 65 will be between those two numbers, right? 80 will be over there. That's 80. Okay. So what I do is, okay, this is not clear enough, so I zoom in and I see that 85 or 65 is, and 65 psia is that dash line. See the diagonal dash line. That is 65 psia. 80 is that line. So that cross point is the initial point. Okay, initial point. Okay, let's go back. This is a graph that you will get in the exam, right? So it may be difficult to read. So you have 80 Fahrenheit, you draw 80 Fahrenheit line. That's 80 Fahrenheit line. And you have 65F, 65F is, that thing is 65F. So that cross is your initial condition. Okay, that is the initial condition. We know that when we calculate theoretical horsepower from the compressor, S is constant. So we go up straight. Okay, go up straight. That makes S to be constant. When do we stop? We go up and we stop at the target pressure. Our target pressure is 215, right? 215. We want to compress from 65 to 215. So 215 is the target pressure. We go directly up and stop at 215. Okay. So I stop over that. My task now is to read left axis. Okay. So left axis is where's sign up sheet? Everyone signed it? Who haven't signed it yet? Everyone signed it? Can I have it, please? Adam Strong. What is left axis? This one. Small h or capital H? Small h, because it's per bar mole, right? Because it's per bar mole. So what I do is, I have initial condition and final condition and read the value on that axis. So one of them I get 400, another one I get 1,800 BTU per bar. So now we know how to get this number, correct? After we get this number, look at the formula. The amount of work is the difference in the specific enthalpy multiplied by number of mole being compressed. Then we will get horsepower, kind of horsepower, right? So what I have to do is, I need to know how many mole, how many bar mole that is for 1 mm SCFD. I have 1 mm SCFD coming in. Okay, 1 million standard cubic foot per day. So how many bar mole per second? So how do I do that? We did this early on, right? And we can do it several ways. Right now, I show you how to do it by use just PV equal to nRT. So N, number of mole. Z is 1 because that's 14.74 psia and 60F gas have compressibility factor equal to 1. So P is the reference pressure. V is volume. We have 1 million, right? We put 1 million. Okay. And R is 10.73. T is 60 or about 520. Okay. Put everything together, I get that much or that many mole per day. So I have mole per day. Next step, I have to multiply by delta H. Okay? Because my equation look like that. N delta H equal to minus W. Okay? So I get N. And now I have to calculate the compression work. The work done by the compressor on the system. So I use N multiplied by delta H. So I get that many BTU per day. Okay, it's not a horsepower yet. Sad, right? We do many things but we don't get the answer. A little bit more, okay? Now we have to convert BTU per day to that horsepower, okay? I give you this conversion factor and we'll give you again if you need it. You don't memorize this, but it's easy to memorize. We know that 1 horsepower equal to 550 pound-force foot per second. So horsepower is the unit of power. Power is energy per time, right? That is power. So energy is pound-force foot and divided by second, then we have that relationship, 550 pound-force foot per second equal to 1 horsepower. And I also give you another one, which is 1 BTU equal to 778 power force foot. Okay, so if I want to know, I have that many BTU per day, how many BTU per second? So 1 day has 24 multiplied by 3,600 seconds. Good. So when I add that, it will convert from BTU per day to BTU per second. Then I know that 1 BTU is that much power force foot. So I multiply by 778 to give me power force foot. So next I divided by 550 to convert to horsepower. And then I get 60.5 horsepower. Now I'm ready to select the compressor. Good? You can do this, right? You have to practice. Of course, there's no homework. Where do you have practice? You practice from this example. Will the exam be a lot different from this? Probably not. Okay. Will you practice, please? Okay. All right. Now we have horsepower. This is theoretical horsepower. Please note that this is theoretical horsepower that is not about what type of compressor we use. Do we use a screw compressor, reciprocating compressor? This is not about that. It doesn't take into account of any type of compressor. Okay? It just say, okay, theoretically, if we have reversible adiabatic, that is how much horsepower that we have to go from one stage to another stage. Just that. Okay? And temperature, how do I get it? I read temperature from the chart. So when I go up and I stop at 215, so that line is 215, I go to the left side and try to find out at that 215 how much is that temperature. I get that much, between 200 and 300. So the example tell me, oh, over there is about 230 Fahrenheit. Okay, that is my temperature. Compression ratio is pressure at the discharge or outlet divided by pressure at the suction or inlet in PSIA. So 215 divided by 65 equals 3.3. Good? It looks easy when you go over it with me, okay? But when you do it in the exam, it doesn't look this easy. Okay? So how long does it take, Ernest? How long does it take for you to do this? 10 minutes, 15 minutes, half an hour, 1 hour? 4-5 minutes. Wow, okay. Okay, very good. I've memorized that number. 4-5 minutes. Alright, compression ratio. What I want you to look at this is, you know that when we do the compression, it will be hot. How hot can we withstand? I think 350 Fahrenheit or something. The number is in the next set of slides. But if we have too much compression ratio, we try to go from like 65 psi to 1,000, 2,000, 3,000. We cannot really do that in single stage because the amount of heat that will come out is a lot. Because we have to put a lot of work to the system, right? And the heat will go up a lot. So we cannot do that in just one stage. So compression ratio per stage should be less than 4. Okay? Usually it's less than 6, but the recommendation is practically it should be less than 4. If we have the compression per stage, okay, I will tell you what is the stage. If we have compression ratio per stage more than 4, it's not good because the temperature will be too hot. Okay, the equipment doesn't work that good when it's too hot. Okay, when they design the system, they design at a certain temperature. So when the temperature go up, there has a little bit of expansion and it can melt. And in the field trip, you see that the exhaust gas can ignite and burn the system, which is a couple $1 million. Is it $5 million? No, couple $1 million. It's expensive. Okay. So the compression ratio per stage, not total compression ratio, should be less than 4 to not make it too hot. Alright, compression ratio per stage. How do I get that number? I have discharge pressure in absolute value, psi equal to suction pressure, psi multiplied by compression ratio raised to the power of n. N is the number of stages. Compression ratio per stage equal to discharge over suction to the power of 1 over n. Just do the math. Okay. So if I have 3 stages, I have 1 over 3. My first stage inlet is at 20 psi. I put 20 over there. My final discharge pressure at the end is 1,000. So I put 1,000 on the top. Then I calculate compression ratio per stage will be equal to 3.6. It's less than 4, so it's good. What happened is this. We start at 120. Not 120, 20 psi. Then it go to first stage of compression. Then the pressure go up to be 73.7. The second time, it go from 73.7 to 71. And then we compress again to 1,000. Okay? So we have 1, 2, 3 stages. Good? Okay. So this is, now you can do this example, right? If I tell you, okay, how many stages do I need and what is the pressure after each stage, then you can do it. If I have 3 stages, then you know that the pressure should be like this. I put over here that the total power is a minimum when the ratio in each stage is the same. And in our compressor, the ratio in each stage, they are the same. Okay? So typically they design it like that, so that the total power will be minimum. The power required to do the compression. 2-stage compression. Let's go back to the diagram again. So I put here that addition of the interstage cooler give a more efficiency. We have quiz at the end, okay? 10 points. If you go anywhere, come back before last 7 minutes. Look at this one. You should be fine. If you listen to me throughout this class, you should be fine. So you should pay attention, okay? All right. So we have volume and pressure. We have starting point. So this shape is the work done for the first stage. Okay, work done for the first stage. Once we finish the first stage, then we cool it. We cool it so the temperature go down while the pressure stays the same. You see from point A to point D. Point A to point D, I have pressure stay the same, right? Because this is the pressure, but volume go down, so it shrink. So when it go to another stage, pressure stay the same, but it shrink a little bit. When it shrink, then we go to the second stage. We do the compression again. Look at the shade area. Shade area show us that is the amount of energy that is saved by cooling it before compress again. So we should cool it down to save the energy. In addition to that, if it is too hot, the material cannot withstand that kind of pressure and it's not that efficient. Okay? So when we do multi-stage, we cool it before we do the next compression. When we cool it, we may have some liquid condensed, right? So what we will do is, we do the first stage of compression. Step number 1, we have a separator or knockout drum or scrubber. Scrub any droplet out. Then we go to number 2. compressor. So we increase the pressure from A to B. After we compress, then we cool it down. Number 3 is interstage cooler. Okay, number 3, we cool it down. Once we cool it down, something will condense, some liquid condense. So we have to scrub it again. Number 4. Number 4 is a separator or scrubber to remove any liquid droplet. Once we remove liquid droplet, then we can compress it again. Number 5 is a reciprocating compressor. So we compress it again. When we compress it, we cool it again. We remove any droplet that condense after the cooling, and then we are ready to go. Done. Okay, that is the diagram. So in Mollier diagram, we go from point A. So point A to 2, theoretically we have constant entropy. We just go up, right, to point B. At point B, we cool it down. During the time that we cool it down, the pressure stays the same. Okay, we don't lose any pressure, but it shrink. Volume go down. Okay, so we follow the constant pressure line from B to C. So that BC is the constant pressure. Let's go back to the Mollier diagram. So this is a PSI absolute pressure. And that line, diagonal line from top right to bottom left is a constant pressure line. When we move through the interstage cooler, theoretically, we have constant pressure. We follow the constant pressure line. So this is a theoretical value. Okay. In reality, you may have a little bit of pressure drop, right? Whenever you flow through a pipe, you have elbow, any turn that you have pressure drop. Okay. So once we pass the interstage cooler, we go to number 4. Number 4 is to remove any droplet. Pressure, temperature stay the same. So we compress it again, so it go up. Okay, straight. S constant. Then we reach point D. Once we are at point D, we cool it down, then we get point E. So this is how the Mollier diagram is related to the diagram above. In Mollier diagram, another name you would say Enthalpy diagram. Entropy is on the horizontal axis. Okay. Everyone is good? Are you ready for the quiz? Probably, okay. The quiz is very easy because we cannot do any makeup or anything anymore. Okay, look at this one. Cooling or heating a gas at constant pressure. So when we cool the gas at constant pressure, we follow the constant pressure line, right? What I do is, okay, I use example 3.6 from Ikoku. A, the question here is, what is the amount of heat that must be removed in cooling 1 pound mole of 0.6 specific gravity natural gas at 200 psi from 600 to 100? So what I do is, I read the chart and find that two number, H1 and H2. Okay, find that two number. So 600 psia from 2 psia, 200 psia, 600 to 100. So I read the chart. I find first point is the start point. Okay, 600 Fahrenheit, 200 psia. It is over there. How do I know that it's 600? So I read the bottom one. So that is 10,000, 5,000, 2,000, 1,000, 500. That is psi, right? I need 200 psi. So 200 psi is that line. That thing is 200 psi. Okay. And I need 600. So I have 500 over here and 600 Fahrenheit. So my 600 Fahrenheit is over there. So my start point is from there. That is my starting point. and I want to go down to 100 Fahrenheit, but constant pressure. Okay, so I identify my 100 Fahrenheit. So 100% Fahrenheit is over there. Constant pressure is the dashed line. Dash red line is a constant pressure. So if my interstage cooler move along that line, I will have the difference of enthalpy from 6,100 BTU per pound mole to 500 BTU per pound mole. So 6,100 minus 500, I get 5600 BTU per pound mole. That is the amount of heat that must be removed. Can you do this? No homework for you yet, but this is on today's lecture. Okay. Okay. Question B. If this gas is then heated from 100 to 300 F, so we heat from 100 to 300 F, how much heat is required per pound mole of gas? So we heat it at constant pressure. If we heat it, so this is just the example. In reality, we don't really heat it at constant pressure like this in the gas compressor, right? But we can still do the calculation. So when we go from 100 to 300 F, so I go up with the constant pressure line, right? Constant pressure is that red dashed line. I go up and I stop where I reach my final temperature target, which is 300. So I stop over there, and then I read my small h value from the left side. Okay. So I get 2,600 minus 500. So I get 2,100 BTU per pound mole. So this is heating and cooling at constant pressure. Question. How many questions like this in the exam? I don't know, I haven't made it yet. Okay. Alright. Next step, I also want you to, okay, maybe take a break a little bit. You ready? So this will be a little bit of math. Okay? A little bit of math. The objective here is starting from here to get this equation. This is to get this equation. When you look at this equation, it's a nice equation. Instead of reading the chart doesn't give you that much accuracy, right? I can tell 6,100, but I cannot tell like 6,170, 6,130 or something. It's difficult by looking at the chart. Okay. This thing tells you right away, if I heat from pressure 1 to pressure 2 without using the chart, how much is the theoretical horsepower? Okay, that is the objective. We try to get that. How do we get that? Or where is that from? Okay, where does that come from? Let's start. So we start from conservation of energy. This time, we write a full form. Okay, we have delta U. The change in the internal energy is related to the change due to temperature. Integration of TdS is delta U, okay, plus P dV minus P dV, yes, and sigma dA mu1 dm1 mu2 dm2. Sigma this thing is the change in the internal energy due to the surface energy, surface effect. Okay. P d minus V is a change in internal energy due to compression effect. Mu1 m1 is the change due to the change in the composition of substance or the chemical potential. It may look like very long, but we neglect several terms. Okay. Increase in U due to heat required or due to heat is equal to the sum of heat absorbed from the surrounding Q. Another energy, irreversible dissipation WL. So I write this. The change in temperature is about, so how can we have the temperature change? How can temperature go up? temperature should go up because of work or friction. WL is a loss, right? Irreversible dissipation, which is kind of friction, right? And Q is the heat from the surrounding. So those things cause the temperature to go up. I substitute this thing back into the previous equation, into this thing, delta U. Delta U is defined by that long 1, 2, 3, 4, 5 term. Okay. I substitute it back, so I have Q and that Q. Okay. I note here that WL is a lost work, energy that could have done work but was dissipated within the flowing material. Is a lost work, okay, due to friction. So Q cancel with Q, right? Make sense? So that Q gone, and we neglect the term containing sigma and mu, chemical potential and surface energy. We said that the energy related to other term is way more than change in any chemical potential or surface energy, so we neglect those terms. Then we just have 1, 2, 3 terms on the left hand side and these two. Next, we assume again that the change in kinetic energy and potential energy and the energy loss is negligible, so we don't worry about energy loss and we don't worry about any of that. Then we have this thing. Minus W equal to integration from 1 to 2 VdP. 1 to 2 is from suction to discharge, or stage 1 to stage 2. Okay? So that is minus W. Okay? So W is the work done by the system, minus W is the work done on the system. We are still good? Okay. So when you know how we derive it, then you will know what kind of assumption is related, associated with this, right? So we assume nothing to do with elevation change, nothing to do with the velocity change, and we neglect any work loss due to friction or anything. So this is kind of a theoretical power, okay? Theoretical horsepower. Okay, next step. We say, okay, it is a reversible adiabatic. Reversible adiabatic is constant S. Okay, constant S. I see you do this. Okay. Constant S. Isentropic process. PV to the power of K is constant. Okay. What we do is, I put derivative term. I put small d on the left side, small d on the right side. D of constant is 0. D of something multiplied by each other is PdV plus VdP, right? So I get first term and second term. dV, of course, you take the exponent down, and instead of k, you write k minus 1. You have that, right? So divided everything by v to the power of k, you get that equation. Rearrange it and integrate it, you get that thing. Okay. Rearrange it again, you get P2 over P1. So one of them is suction or discharge, it doesn't matter, okay? You can switch it and it's still correct. It just move from stage 1 to stage 2, or maybe it's matter. When you move from stage 1 to stage 2, the pressure should go up, okay? So P1 should be the stage 1, which is low pressure, and P2 is stage 2, which is more pressure. So you get this equation after you integrate it and rearrange it. So P2 over P1, the ratio of pressure equal to the ratio of volume multiplied by raised to the power of minus K. And K is Cp over Cv. Okay? We assume isentropic process. So Pv to the power of K equal to constant. So if you move from P1 to any pressure, you get volume at that pressure P divided by volume 1 to the power of minus K. So this is for any isentropic process. Okay? So we make note of this and we will use this to substitute back somewhere. Okay? And we start again from 1 over P dP equal to minus V over K dV. Integrate it again. So this time I move, last time I separate the variable and integrate, right? P with P, V with V and integrate. This time I move V to left side and P on the right side. Okay, right hand side, K is constant, I take it out. And that pressure, I use this formula that I just got, substitute it back with that P. I put everything back, so I get P1 multiplied by V over V1, everything to the power minus K. Okay. And from conservation of energy, we know that minus W equal to integration from point 1, stage 1 to stage 2 of VdP, right? I substitute it back, I have this. Okay. Then integration of VdV, I put, this time I use this relationship. So I have, let me clear everything. I go from here to here, change from dp to dv, okay. Rearrange it somehow by use the relationship that we already have early on. You see this one, right? dp equal to minus pk over vdv. Substitute this back over there, or use the original equation on the top. That one. So sleepy, right? This is just a derivation. Okay. Of course, you can go over it. How do I know that you can go over it? I don't. Okay. But at least you should be able to do derivative or something. Okay. A little bit more. We rearrange it. We integrate it. Then we get that form. Okay. After the integration, we get that form. And we rearrange it again. Almost get the final equation, that one. So look at this block on the right hand side. It's not the final form yet, but it's a form that it has a unit consistent. When all the unit consistent, W is not bar force per foot. Okay. If you put W as bar force per foot, we need G sub C, right? So that W in the right hand side box is not bar force per foot. It should be something else. Okay. So something else is that something else. That W is bar force foot. Okay, we don't use BTU yet. Or if we use bar force foot, we have G sub C. I have seen some conversion factor that we put later. So the unit of this thing has to be unit consistent. So P, V, everything should end up with W. We define W as work, or W is bar force foot. Is it unit consistent? Marcos, can you help me?
Yes.
Okay, I get this from Ikoku, and I think it's unit consistent, but at the end we have some term pop up. Okay, many terms, not just some term. So we change from that W to be work per unit mass. Okay, change to work per unit mass, and I get that equation. So I think W is bar force foot, and the unit of everything in here is the same as the unit that we used earlier. Okay, now it should make sense to you. Is it? So it should have the same unit as this whole thing, because we start from this equation. Now we good? Okay. Next step is just the unit conversion. Okay. We try to go from that box on top left to this thing on right hand side. So what we do is we express W is work, right? W bar is work per pound. work per unit mass. Use PV equal to nRT and express R in the unit of, this time we don't use 10 point something, we use 1,500 pound force foot per Röntgen per mole. Because on the top we use pound force foot, not BTU. If we use BTU, it will be something else, right? So when we do this is a unit conversion, and gamma, that thing is to express molecular weight as a specific gravity multiplied by 28.97. Ikoku get 35.241. I didn't get that. I get 53.341. Ikoku get 53.241. I think it is a typo. If we use 33.241, that's equivalent to molecular weight of 29.026. It doesn't matter, okay? This unit doesn't matter anyway. So when we do the unit conversion, we get that equation almost ready, except